So welcome all of you to this extra day of the course on rock slope engineering. And this will be a shortened version or the curtailed session and just focusing on one remaining tutorials, which I promised to do. And today I'm going to fulfill my promise. And thank you very much for making time for this extra day actually. And so without taking much of your time, I'll straight away go to that tutorial. And I have put it in a combination of PowerPoint as well as hands-on so that you understand it. It is a very interesting tutorial and a very important one. So let's get started, for which I have to share my screen as far as the PowerPoint is concerned, first of all. And so there it is. We are going to discuss or see how to design a bench, which is bench design in the software called RocPlane. RocPlane is the software which is used to analyze and design slopes affected by a planar failure. Okay, so we'll see how we can design a bench. Let's put things in perspective first. The figure that you see on your screen, we'll revisit it 2 or 3 times in the presentation. We'll come back to this. There are some very important aspects of bench design mentioned on this figure. Okay. And so the best example of a benched slope is always from an open pit mine. It doesn't mean that you don't have bench slopes. Tall, high slopes in civil engineering, they are usually benched. But this bench design is so much more prominent in a typical deep open pit mine that it's good to have an example from open pit mine. It's the same thing basically. Okay. So this tutorial will familiarize you with the bench design features of RocPlane, the software, by analyzing an open pit. Okay, now topics which we are going to cover in this tutorial are, we'll see the random variables, which is part of the probabilistic analysis, persistence analysis. You will see if a joint which is, or a discontinuity which is persistent. Now it is, by now you should be able to realize that the joints which do not persist or do not extend to longer distances versus those which actually persist, the instability or the stability would be different in both cases. We'll see that. Bench loss. Now bench loss, yesterday we mentioned it slightly. When you have this bench like this, and or if I go back to that picture, although we come back, that the red one, the red portion, the edge, the crest of the benches, this is likely to give way over a period of time. And this tumbles here. This can, the instability, the failures can happen here, because of which this back break, what's called back break in mining engineering, that thing has to be kept in mind when you want to design the minimum width of the bench, because this eventually will be lost. This part will be lost eventually because of several reasons. Wherever you in rock engineering, you have these corners, sharp corners, you can expect problems there, where stresses are likely to exceed the strength at the corners. Anyway, so we'll come back and see this. And we'll see the managed slope design approach. These things that we are learning, slope engineering or tunneling or whatever, the geotechnical, it's a very practical science. It's a very, especially rock engineering is even more practical. And so one must also know that how things are managed at site, how things are done at site. And, the effort of more and more developers of software is towards that the software should be able to simulate the conditions which happen at the site. Actually, when you start using the finite element programs, you will see how effective they are in simulating the conditions. But in RocPlane here, when I say managed slope design, I'll explain to you what I mean by this managed slope. It's an approach in mining engineering, which we are trying to incorporate in the software. And then finally, we look at the quantitative hazard analysis and see, we will see when we come to it. Okay. Now slope instability in open pit mines or any benched slope, there significant design challenges are there for this. For example, any failure of slopes in such cases can be controlled by major structures. You can imagine that, like a big fault zone, big lithological contact between 2 units of rock, which are extending for a long length, sufficient length, and they can affect the overall stability of the mine or of the slope. Okay. Or they can be affected by smaller structures such as joints, foliations, bedding planes, etc. So there could be very large, structures which could affect the overall stability of the mines, or smaller structures. So as far as the large are concerned, in fact, during one of the presentations, you saw deep mine in which you had this spectacular failure when we were talking of sliding. I hope you remember that picture. It's one of my presentations. Huge failure, maybe a kilometer deep mine, and you see this failure. So for that kind of failure, large scale slope failure, there are tools available, such as the one is slide 2, which is there part of a suite, and slide 2 is the one on which we are going to have a webinar, and you received the information about that today on 3rd of June. So those tools are available, and you can design, and in fact that design has to be carried out for large mines. But then when you use that, unanticipated instability can happen on the benches, the small scale instabilities, not the large scale, small scales. You must also pay attention to these small scale bench level instabilities, which can happen at local benches. And those small scale failures can have a direct influence on the overall slope angle, because bench angle has a relationship with the overall angle. So while you are analyzing the overall angle, the bench angles should also be analyzed. The bench level instability should also be considered, because it affects the overall stability. And RocPlane, which is what we're going to discuss, includes a bench design function, which allows the user to assess the stability of bench scale wedges, the wedges formed at the bench level. For a range of face angles, you can change the face angle and see how the wedges are formed, how these wedges are affecting the stability at the benches. So for doing so, the two design approaches are available. One is a managed approach, which I mentioned, which I'll explain. Managed approach to slope design, and second one is a quantitative hazard assessment. We'll look at both. So by using the managed approach, the user is able to assess the number of failed wedges and the minimum bench width required. Okay, because minimum bench width is one which fulfills the functional requirement, taking into account the width which may be lost due to bad break, and the width which may be lost because of material spilling from the bench above, which is part of managed approach. I'll explain in a while, don't worry, I'll explain. Okay, for making a quantitative assessment, you want to talk in terms of numbers, so quantitative assessment, the user is able to estimate the chances or the probability or the likelihood of forming of different wedge sizes, which is called probability of occurrence. What is the probability of occurrence of wedges? Wedges will occur or not. And another probability is that whether these wedges which have occurred, which have been formed, whether they will slide or not, which is called probability of sliding. So first, probability of occurrence of wedges, and second, probability of their sliding. So these two things provide you with an estimate of the probability of failure. And we'll see that by the time we reach the end of this this tutorial, you will see that we'll look at the probability of failure, which is based on the probability of occurrence of wedges and probability of sliding of those occurred wedges. Okay, and so both these approaches, the managed approach and the quantitative assessment approach, they provide valuable information about the bench loss, how much bench loss will happen, and they help you, the user, the designer, in selecting an optimum bench face angle. Okay, we'll see how to do that. And now's the time we'll keep moving between this presentation and the software. So move to RocPlane, which is the software, and return here later. Okay, so I will stop here, stop the share, quickly go to the software, which is here, RocPlane. Okay, so as you know now, you are all experts. File, new, something opens, which is based on the default data. Factor safety 1, we are going to change this. And the rest of the things you've seen. So we go straight away to analysis and project setting. Today, what we are going to do, we are going to select probabilistic analysis. Because as I told you, in actual practice, you will be, and you must, and you should be making extensive use of probabilistic analysis. In geotechnical engineering, you are always dealing with a range of parameters, and you are seldom, very rarely sure about the exact value. Okay, so probabilistic analysis. Now this particular tutorial is kind of, we're moving towards practical aspects of things. Okay, and so we'll choose probabilistic analysis. Units are fine, and since we have chosen probabilistic analysis, these would come into picture: sampling and random numbers. Let's go to sampling, and you can choose one of the two methods of probabilistic analysis available: Monte Carlo. Remember those gambling casinos of Monte Carlo? And Latin hypercube. We'll choose Latin hypercube. You can also run the same analysis in your leisure time, choosing the other one. Okay, so and number of samples, let's make them 100,000. Yes, 100,000. So many samples will run. And factor safety, let it be 1. You can actually change this if you want that you're not going to accept anything below 1.5. You can change it here, but we'll leave it 1 for this tutorial. Okay. And as far as random numbers are concerned, see, although this tutorial is a little advanced than the tutorials we did, but it is not the most advanced in the sense that you still have to do a lot of self-study. For instance, when we go to random numbers, you have some options here. Pseudo random, constant seed value, what it is. Actually, you should read about it, go to help menu, but some help is available here. Pseudo random, each time you run an analysis, you will get exactly the same result for a given seed value. Okay, which means reproducible results. If you don't check it, you may get slightly different results all the time. Why you get it, why you should get it, actually in the final thing, it doesn't matter that much. You can always choose this. But for advanced study, you must know about this. Okay, and what is a seed thing? So you must read about it. I'll leave it for you, but for most of analysis, you don't have to worry about it. Okay, but to be a good designer and somebody who knows in and out of your software, you should later on, you can go and read about it. Okay, and then random should not be chosen, which means this is a random number. We are again skipping this. Then there are some number generators here. Again, this is random and Park and Miller version 3. Not really necessary for this level. Okay. Perhaps never. You may have to read about it later. So we'll skip for now. It's not related to the geotechnical kind of thing. Okay, so what we do, we design standard we are not choosing. Although, if you're really interested in Eurocode, you can run another tutorial on Eurocode. So we'll just check random is fine, pseudo, and I think it's okay. Okay, so we go to just okay, and we go to input data, analysis, input data. Okay, and once you go to input data, we have so many tabs here, and we are not doing water seismic forces. There are more tutorials on all these things. We are skipping that, otherwise things will become complicated. We just want to focus on bench design. So whatever minimum is required to understand bench design, that we'll do. Okay, so what we'll do, we'll select this the slope angle, mean value 60. Remember, we are talking of probabilistic analysis, so it will ask for mean value. But what we are not going to use probabilistic analysis for slope angle. So this mean value actually becomes the exact value. If you give it a variation like these, remember we gave normal variation that day, we are not changing this. So although it is mean value, it becomes the actual value of the slope. Also the height, we will not change it. You can do that actually, but it only make your exercise complicated. As I said, right now we want to focus on the bench design, and whatever minimum is required for bench design, we'll do that. So as far as slope tab is concerned, which 60, 15, and none, no variation. This is fine. And this is something we'll specify here. Minimum wedge size, although you can read about it, but you can give it a weight. We have given it a weight, 0.001, which means that any wedge which is smaller than that will not come into question. So what we want to do, we want to avoid, ignore small wedges, because there are many small wedges which may be formed. Because in this tutorial, later on the option will come, we're going to choose not very persistent, but small joints, the possibility of existence of small joints. That might also form number of wedges, which will bother us unnecessarily. So we are just avoiding these smaller wedges, but you can run the analysis without checking this also and see the influence. Okay, for now we are saying that anything smaller than this, we are not considering that. Minimum wedge is at least this. Okay, and then we go to the next tab, which is upper face, the upper face. And the upper face, we make it horizontal, so 0, and we are not giving it any variation, so it's fixed at 0. And the bench width, remember we are talking of bench here. We're talking of bench, and if you're using this analysis for bench, then usually the upper face would be horizontal all the time because benches are horizontal. Okay, so the bench width, yes, we have to specify. Let's specify 7 meters for this. Now 7 meters is a pretty common bench width, 5 to 7 meters, because it also has to serve a functional requirement. And okay, so that's fine. I think we don't change anything else. We are not giving any variation to the bench width also. Then we go to next step, failure plane, the plane along which the wedge can slide or block can slide. Okay, we give it an angle, mean angle of 55 degree, and this we are going to vary on a normal variation, and the standard deviation is 10. These are the input parameters given to us, and this will become 30 and 30. So the analysis will run the angle and check the angles of these because we want to see the angle that we have to vary from 25 to 85. 55 minus 30, 55 plus 30 in steps of 10 degree. Waviness joints, we can give it some value, mean value 10 degree, waviness of the joints, and uniform distribution, which means you only have to specify the minimum maximum 5. Okay, 10 30 30 10 5 5. And now let's go to the next step, strength. More Coulomb, you can choose Barton Mendes, etc., etc. Let's choose more Coulomb to keep the thing simple. So you need C and phi values, and you can choose parameters. You can also choose strength, which means you'll ask only for strength, but you can choose parameters here. Okay, so it asks for, this will allow you to vary the cohesion and friction angle separately if you want to. Probabilistic analysis. You can see, you can give variation to cohesion and friction. If you choose the strength, you can only vary the final strength. Okay, that option is available. So let's put the cohesion as 0, and we are not going to vary this, and we are going to put the friction 35 and give a normal variation here. Normal distribution with standard deviation 3, and this is 9 and 9. So the analysis will be run taking into account a range of friction angles from 35 minus 9, which is 26, to 35 plus 9, which is 44. Okay, and that's about it as far as the strength is concerned. Let me check. I could have, I have a file available here. If I recall that file, all this data already there, but I just want to one more, since we're starting after some gap, just want to take you once more through this. That's why I'm doing it manually. 399, and that's done. Okay, now we are pretty much done. Tension crack, quantity water, forces, seismic plane water, we are not considering for this analysis. Okay, so okay, and you see the analysis result. You see probability of failure is 0.600. At this stage, let me go back to the presentation where I'll discuss all these things. So let me go back to that PowerPoint presentation. Okay. So you saw the probability of failure as 0.600 something. And what this analysis did, which we've just run, computation of 100,000. Because remember, we specified those many samples, 100,000 Latin hypercube samples occurs, and the probability of failure, which you saw calculated, was 0.6004. And the results of probability analysis are summarized in the sidebar information panel. This is what you saw actually, 0.60041, and that's where it is summarized. Probability of failure 0.60041, which is actually 60.041%. Okay. So in the sidebar, the wedge computed using mean values of all input parameters displayed along with its factor safety. So what do you see here? This wedge, this is the mean wedge. Although we ran an analysis with some of the parameters, we gave a range for some of the parameters. So you should obtain several wedges, actually 100,000 wedges. But the mean wedge is being shown here. Mean. You know, mean wedge means average wedge, not the mean. You know, we call some people, how mean is that person? Not that mean, you know. So not that. This wedge is our friend, not mean. So it's mean average. I hope you know that. So and that's where the data is. Sorry. The mean wedge data, factor safety of the mean wedge, taking into account the mean values of everything. Okay, but let's go back. Total probability of failure for slope is 60%, which means out of the 100,000 samples, 69,160 produced valid wedges mentioned here. Number of valid wedges 69,160. Okay, number of failed wedges 60,000. So 60,041 divided by 100,000, that's the probability of failure, which is mentioned here. 60,041, which are failed wedges, divided by 100,000, 0.6004 or 60.04%. That is the probability of failure. Okay, I will send this presentation across to you. Now, this is about the mean wedge. As you just saw, the factor safety for the mean wedge is 0.6138. Now it is important that RocPlane, the software, tries its best to fit the wedge inside the slope dimension, whatever slope dimension we specified, you know, the slope angle, upper slope, etc., the height. So it will try its best to fit the wedge there, which means RocPlane tries to determine a maximum size wedge for any slope geometry. That for this slope geometry, which the user has specified, what is the maximum possible size of the wedge? So probability of failure, which you get 0.60041, that probability of failure is conservative, which means upper bound solution. It is on the safer side because the positional information of and joint length is not accounted for. The length of the joint, how persistent the joint is, etc. That those are not, and where exactly this position not accounted for. And the maximum possible size. So the focus of the RocPlane is thinking like humans, is on fitting the wedge. The software thinks that this user has specified this much, you know, size of the geometry of the slope. So the whatever the maximum possible size of wedge is there, I'll fit it. Now that kind of a size may not be formed. So you are getting a probability of failure, which is on the higher side. Actual probability of failure may be less. So how do we incorporate these? How do we make it more realistic? How do we incorporate the, you know, the persistence and position and size of the joints, etc.? This would be addressed in the next sections. So we will try to address this limitation. Okay, you'll just see. And continuing with this understanding, the bench plays a critical role. As we have mentioned, bench plays a critical role in open pit mining. Okay, and in fact, civil engineers who are building these slopes, they, before attempting, I tell you, my advice, civil engineers who are involved in highway design and the highways passing through mountainous regions, they have all to be sent for an internship with an open pit mining company. They have to spend a couple of months there, 3 months at least, understanding that. And I tell you, because for mining people, it's their bread and butter, the survival, the stability of this. And it doesn't mean that mining people are not, you know, they're absolutely perfect. They actually are. Some of the people, some of them are, they take a lot of risks, but those risks they take within limits. They know what they're doing. And I'll tell you about that. The managed slope comes under this. So the bench plays a critical role in an open pit mine because it prevents bench slope, prevents rock falls or any slide, any instability of rock from upper levels, prevent it from going to the lower levels. Now the whole action in mining, the whole focus of mining is extracting that core, that copper, that aluminum, that zinc, that coal, which is what sells in the market. It's all about money, honey, as they say, no? It's that part which is important. In civil engineering, that's not the idea. In civil engineering, civil engineers are more benevolent, more generous. They want to do for the good of the society. I know I'm being mean, not average. I'm being mean by saying so because I'm a civil engineer myself. But I've worked in mining companies extensively. In fact, started my career there. But the nature of the work is that you will not open a mine if you do not have hope of finding that ore or that coal which is sellable in the market. And so whole focus is there. Okay, so there the operation is going on at the level, the bottommost level, they're extracting and all the things are being done. You do not want anything to reach there, any fall to reach there. So these benches, they arrest these slides of fall. So but the bench have to be functional also. You know, the vehicles run on it, people go there, lots of stuff happens on the benches. So the bench has to have a functional width. It has to function. And so there has to be usable width. Now, the width should be such that the bench should function, plus it should have enough width to collect the falling material, and it should account for the possible loss of the bench width because of back break, or what is called crest loss. Here, if you see, look at this bench, anything falling from here, for example, this sliding happening here, this red one drops here, that the spill which is falling onto it, it is actually muck or spoil, but since it is coming from the edge, like water is spilling over, in mining term they call it spill. So you have to account for that spill width. Okay, you have to account for this loss which can happen on this. So whatever left you're left with, you know, in fact that is known as the usable width, but part of it can be taken care of. In fact, mining people are also becoming slightly more innovative these days, and some of the things that you saw yesterday when we were talking rockfall, those drapes, etc., now these are finding their way into some of the mining operations. You want to have a width and don't want to make it too wide, and so you sometimes might drape this, but that costs, everything costs. And in mining, cost is absolutely paramount, because if the cost of operating a mine becomes so high that whatever money you get by selling the ore produced, that doesn't remain viable. So they are very conscious about the cost of operating a mine. And so, but then, so there are some critical cases where those things are coming. Anyway, we are deviating a bit from the discussion, but the fact is that these two things play a role, the spill width and the back break. Okay, so this back break width we have to consider, the amount which can be lost. And this is usually lost in a jointed rock by sliding in planar failure or wedge failure. And a couple more things here. This inter-ramp angle, bench width, and this face angle, we'll come back to this. Okay, just wait, we'll come back. So for a bench design, it is important that you, the engineer, should determine, number one, or A, the number of failed wedges that are expected to occur. Or in other words, the width, the back break width, that can happen, that can be lost. Only then you will be able to design the width of the bench. Because width of the bench will affect two things straight away. If I go back to the picture, it will affect this angle, which is the bench angle, and this angle, which is the inter-ramp angle. Maybe also the height. It will affect those things. So bench width is important. Okay, the number of failed wedges that are expected to occur, or the size of the, or distance of the back break. B, number two, the likelihood, the chances of different back break distances, which means probability of occurrence. What are the chances that the back break distance would be 0.5 meter, 0.6 meter, 1 meter, 2 meters? How much will be the back break? What are the chances? Probability of occurrence, that you have to see. And the software will help you as we go later. See the likelihood or chances that a wedge with a given back break distance will slide. Okay, you have said that, okay, what are the chances of a back break distance of 0.5 meter? You see the chances, 30%, 40%, 50%. And then what are the chances that in that distance will actually slide? Okay. So combination of the probability of occurrence, combination of, and with the combination of probability of occurrence with probability of sliding will give you the probability of failure, which we'll see in this tutorial. So, which is also mentioned in the last point, when the probabilities of occurrence and probability of sliding, they are multiplied together, an estimate of probability of failure is obtained for a given back break distance. And you can then assess at the end of this that, okay, if the back break distance is this much, what is the probability of failure? If the backbreak distance is increased, what is the probability of failure? So you can, it will help you in deciding about a bench width. Okay, so let's go forward, and now the size of the wedges, which will affect the backbreak distance. Size of the wedges is controlled by the slope geometry. You know from the rock plane and the planar failure that depending on slope geometry, the cut slope height, the angle, etc., that would determine the size of wedges. Remember the size of wedges we used to form? Since the size of wedges is controlled by slope geometry, these probabilities, probability of occurrence of wedge, probability of sliding of wedge, will change as the bench face and bench angle are changed. You know, if we change these values, this angle, the probability of occurrence of wedges and probability of sliding of wedges will also change, which means probability of failure will change. Okay, so the goal or the aim of the bench design should be to find out, to determine, to estimate the optimum orientation of these angles. And how do you define the optimum orientation? Optimum orientation is defined the steepest interramp angle which can be achieved while preserving the required bench width. This is the interramp. What is the steepest you can go as far as this is concerned? Anything steeper than that will not leave the bench at optimum. That's what I, okay. Now, there's a bigger picture available here. Anyway, I've tried to explain this. To assist in this assessment, RocPlane allows for the failure characteristics for a number of different bench face angles to be assessed at the same time. At the same time, you can assess the different bench face angles. And software also allows for the creation of more reasonable size wedges using the joint statistics. In the initial analysis that we did, I told you that the software is trying to fit as big a wedge as possible. But now, once the joint information is there, it will try to fit more reasonable size of wedges. And once you specify the persistence, etc., which we will do. Okay, and for that, we have to go to the bench design option, which is there in the software. I'll show you that. And two different types of analyses are available for bench design, depending on the nature of the problem that you have at hand. Fixed bench approach, fixed bench width, and fixed interramp angle. Let's look at the fixed bench width, which means, you know, this is the bench width, which is fixed, which means the interramp angle will be calculated for the given bench width and given bench face angle. Now, what is interramp angle? Let's go back to this. This is the interramp angle. If the bench is fixed, interramp angle will depend on the angle of the face of the bench, this angle, which is shown here. This is the bench. This dark blue is the face, angle of face. And this dark blue is the interramp angle. So if you change this, the bench width is fixed. If you change this bench face angle, these are the changes, these dashed. With each change, the interramp angle will change. If that is the bench face angle, this would be the interramp angle. You can see that. Okay. So this analysis will be used where the bench width is defined. You say the mining management will say, mine management, that look, I need this bench width. I can't compromise because of operational reasons. I have these trucks, these dumper, these loaders, whatever. I need this much of the bench width. So bench width is fixed. You can't change it. So then you follow this approach, fixed bench width approach. Okay. Second approach is fixed interramp angle. For whatever reason, they say the interramp angle, this is fixed. So you can change the bench width in this case. As you change the bench width, the bench width angle will change. You know, different angles. Of course, this face angle cannot be less than the angle of the interramp angle. Otherwise, bench will not be formed. So in this case, bench is not fixed. Bench width is not fixed. This interramp angle is fixed, which means this point and this point is fixed. You can only change this point, which means the bench face angle you can try. For example, from 30 degree to 90 degree, you can try all of them in the analysis. Okay. So in this tutorial, we'll perform a fixed bench width analysis, which is this analysis, fixed bench width analysis we'll follow. Both options are available. You can try. So now again, we move back to RocPlane and return here later. So let's move to that software. Where is software? Here. So remember when we last left this software, we'd done this analysis and we obtained the probability of failure as 60%, 60.041. Okay. And so we continue from there. We'll keep referring back to the presentation. And so the option I told you that we have to choose the bench design option. Okay. Which is available in analysis. Go to analysis and see the bench design here. Okay. Bench design. And there's nothing here. You just check this box and it comes to life. And you can choose the fixed bench width. Remember, you can choose fixed bench width or fixed interram angle. Why I explained this to you? So that you can understand what is the difference between the two. Now you understand the difference. Fixed bench width. And remember, we chose 7 meters. So we leave it 7 meters. We'll say we require 7 meters. I can't do less than 7 meters. We need 7 meters. Okay. So second thing that you need to specify is back break cells. Now, what is back break cells? Every step you have to stop with these software. These software can be irritating, no? But they are such wonderful things because they teach you so much, these software. Absolutely, they teach you so much. Okay, they're better than any human teacher. And you can do in your time, the way you want it. So as they used to say, books are your best friend. Now, these are your best friends. So what is a back break cell? And can I go back to the presentation once more? Let me stop the share, go back to that presentation. And move forward. This is what you just saw. This dialog box just opened there. And we chose fixed bench width. And we specified 7. And back break cells, we got stuck here. So we need to understand what a back break cell is. For calculating the probability of occurrence, probability of sliding, and probability of failure. Just to give you a recap, probability of occurrence is the chances of occurrence of wedges, right? The edge of this bed with the bench, you know, that back break. Chances of those sliding and chances of failure. The chance of occurrence is probability of occurrence. Chance of failure sliding is probability of sliding. Multiplication of 2 is probability of failure. So those 3 probabilities along the bench you want to calculate. To do that, you have to divide the bench in a series of back break cells. And I'll show you the back break cells because that kind of thing will allow you to analyze number of wedges which can happen in one cell. Okay. And the failure characteristics of each wedge like this. Those are the cells. We specify 20, remember? So this is your bench and you can divide it into 20 or whatever number. Like in this case, 4 have been shown. This bench here has been divided into 4 back break cells. Cell number 1, 2, 3, 4. And you can progressively see that how the wedges will be formed in each of these back break cells. Because we want to see the probability of wedges being formed if the back break distance is ½ meter or 1 meter, 1.5 meter. We can do this in steps like this, back break cell. So if we choose 20, we chose 20, no? So, and we know the bench width is 7 meter. If I go back, that's what we chose. 7 meters is the bench width, 20 is the back break cell number of back break cells. So which means each back break cell would be 7 divided by 20, 0.35 meter wide. So each cell is 0.35 meter wide. That's what we are going to, we have told the software. Okay. And let me see if we go back to, okay, we have to perhaps go back. The next thing we have to do is define. If I go back to the software for a while, sorry about this shuffling between 2, but I think that's important. It's not easy, but then I sort of worked it out. And so this was open, remember? 20. Next is define persistence setting, how persistent the joints are. So we go to define the persistence. And there are 2 options, large and small. We'll choose small for this because large is something which is, or large area. We are worried about the small ones in this case. Small, ubiquitous. Ubiquitous is a word which denotes present everywhere, like God. They say, no, God is omnipresent. Everywhere you have God, if you believe in God. So small ubiquitous joints means they are present everywhere. You have joints, several joints. That's what small joint do. Okay. Now, if I go back to that presentation for a while, I think there's some information there. Yeah, I think you can see that. Oh. Just a minute. Now I can do that. I can do the share once again. Share and yeah. Yes. So you saw that dialog and you press define and you saw the options. This option you saw, large and small ubiquitous. Okay. RocPlane looks at two possible conditions for joint spacing. When the large and small is with reference to spacing, you see joint spacing, how far or how closely spaced their joints are. Now, joint means discontinuities, but you know, it's simpler to say joint. But whatever simplicity you got by calling it a joint, all of that has gone out of the window because of this word called ubiquitous. It is not easy to pronounce. Ubiquitous. Okay. RocPlane looks at two possible conditions for joint spacing. If the spacing is large, the joints are, you know, the spacing between the two joints are large. That means that there is only one trace of joint on the slope face. Then in a large joint, how the software takes it, if you specify joint, then the user thinks only one joint will be crossing the slope face. Another joint will be far away. So only one wedge is generated on the slope. And then location and the elevation of the bottom of that wedge is randomly chosen on the slope face. Okay, which is not what you want actually. The persistence in that case will be sampled for the wedge. Okay, but if you choose, and in fact, when the persistence is not large enough, the wedge may be invalid. So what you usually choose is, just to cut the long story short, let me, just a minute. So it's better to choose the smaller ubiquitous joint spacing. Now this, once you choose that model will automatically scale down the wedge size until the persistence conditions are met. Whatever persistence you give, the wedge will be formed accordingly. So which means a wedge is almost always formed whenever you run the analysis. If the slope geometry is such that the slope geometry and the joint geometry is such that the wedge is being formed kinematically. Okay. So it is on the safer side that you are designing by choosing the small ubiquitous joint. If you choose large, you might miss. In case there are smaller joints which are forming wedge, you might miss that. So it's not going to be a safe design. Okay. This is another one. Okay, this is what I meant. Now in RocPlane, the definition of joint persistence, which you will define now, is two-dimensional and is simply equal to the failure plane length. That's the persistence once you choose failure plane length. Okay. And let's move back to that software once again. Okay, so that was the dialog which was open. We chose small and say, okay, we're not activating these things. We'll come back and activate this a little later. Okay. Now we choose the bench face angle range. Now, because I gave you that example, you have two options, fixed bench width or fixed inter-ramp angles. For this tutorial, we are doing the fixed bench width. So when you keep the bench width fixed, you have to change the face angle. Okay. So you can change it from whatever range you want. Let's change it from 30 degree to 90 degree and see the influence of this. You can always change this, and intervals of 5. You can also change that. And then there's a thing called design threshold. You can read about this, but there's some help here. Threshold is typically between 75 to 85. So we keep it 8. What is a design threshold? You know, it's commonly associated with cases where the assumption is that there's infinite persistence of these joints. Now, if you feel that if you know that persistence, if you know that, very surely how much is the persistence, is it infinitely long or whatever, then this number will be higher. You can keep it 100 if you're very sure about this. But normally it's very rare that one would be sure that joints are persisting, and I know they're persisting for so many meters. Rarely. So usually people have seen you keep it with 75 to 85%. If you have very little information, you are just blindly designing some slope and you have no idea about whether the joints will be persistent or not, then this design threshold will drop. It's basically how much confidence you have in your assumption that these are persistent. So if you don't know anything, just keep it at about 80 degrees. Okay. So if I say okay, it will run the analysis. You see it's running. Things will not change in terms of results here, but let's examine the results. And for that, let's go back to the presentation. Okay. So we've again computed for 100,000 because that is what we had fed into this samples. For each bench face angle changed from, remember we gave the 30 to 90 degree, the bench face angle in steps of 5. So 30, 35, 40, 45, all of those. We'll see the results. Now during this assessment, the software was each valid wedge which is being formed, that is assigned by the software to one of the back break cells. Remember we created 20 back break cells depending on the width of the wedge measured from crest. For instance, during this process, the analysis you just saw the software was running, we have not seen the results yet. During the process, if the software finds that a particular wedge which is being formed at any of those angles has a width, as an example, has a width of 0.4 meter from the crest. And you remember we chose 20 back break cells and we also calculated then a width of 7 meter bench width. 20 cells means each back break cell is of 0.35 meter wide width. So a wedge which is 0.4 meter from the crest will fall in back break cell number 2, which is from 0.35 to 0.7 meter. So that wedge will be assigned to the back break cell number 2. That's how the software works. And now you've got the result. I mean, you've got the results. We have to see the results. So there are a number of approaches available to interpret the data from the results. And these include a managed approach as well as a quantitative hazard analysis. Remember in the beginning of this tutorial, I told you there are 2 approaches. And I'll tell you what a managed approach is. Now is the time to tell you about this. Okay, managed approach. Very interesting. In open pit mining, it is often acceptable to use steeper bench face angles, even if it is resulting in some fall, as long as the safety is compromised. They say some little fall which keeps on happening, we'll clear it. It's an operational mine with all the people, workers, laborers, vehicles, all the paraphernalia is there. It's no big deal for the mining management to clear off these things, as long as they are not jeopardizing the safety of it. So small material which is falling can be cleared off. Spill width, remember that spill width? Because if you do not want even a stone to fall, you may have to cut it a steeper angle. One bench steeper angle, the next bench steeper angle, the whole overall slope angle will change. It will mean a huge amount of expenditure also. So every degree of slope angle results in additional cost and additional space on this. You know, there's a place called Goa in India. You know about it. I'm sure most of you know about it. And Goa is a typical place, which is also very rich in mineral. There are lots of iron ore mines in Goa, and Goa is a place where tourists go and it's a habitated place. It's one of those rare examples when you have mines in the middle of habitation, these open cast mines. And they have a typical problem. They can't go wider than a certain angle or certain width at the face. In fact, they struggle to find space for the dump slopes because the material that you extract, you have to dump somewhere. It's a problem. So Even for dumps, they can take it vertically high, but not so widthwise. So they keep thinking about innovative ways of making those dumps stable, and also their minds that way. So if you cut it steeper, cut it flatter, the whole things change. So mine management accepts that as long as the only loose falls happening here and there, and we are able to arrest them on benches and clear them off, it's okay. So that's called the managed approach. They manage it, okay. And this is pretty much the case around the world, because the cost of cleaning up this material is much less than excavating extra rock. And this approach is utilized in RocPlane, managed approach, through various plots which you are going to see. The first plot is called total probability of failure plot. We'll just go back to the software to plot this. We've already done the analysis. This is one of the ways of looking at the results. Total probability of failure. Now this probability is calculated for each bench face angle, 30, 35, 40. Remember we gave the range? By dividing the total number of valid wedges with valid wedges, those wedges which are valid and having a factor of safety of less than 1, which means failed, dividing that number by total number of samples, and samples is 100,000. So that is the total probability, which is plotted. We'll go back and plot this for our case. And this clearly shows as the angle of the bench face increases, the total probability of failure also increases, which is quite logical. Now let me stop this and go back to the software just to show you how we obtain this. Go back to the software. We have run the analysis. Now is the time to look at the results. The first thing we're going to see is go to statistics, go to bench design, and the very first thing, total probability of failure plot. You get this, which you just saw. So more clear though than that, as the bench angle increases, the total probability of failure also increases, which is quite, logical. So as I said, that you are prepared to accept a situation where there's some fall, some spill, which will clear off. How much is that? Depends on how much probability of failure you are ready to live with. For example, you say, I'm fine with 20% probability of failure. So you would like to know what is the bench angle for that kind of failure. So go to sampler here, show sampler, go to 20%. This, let's see, where does it hit this 2020 and 49. So up to 49 degree is okay. You can accept that. Anything steeper than 49 degree would mean the probability of failure will increase. So if you say, I'm ready to accept 20% probability of failure, which means you can go up to about 49 degree of the bench angle. That's what you say. So you cut the bench at 49 degree, which will result in some failure, which will clear off. That's the advantage of this. If I go back to this, the presentation once again, that's what it will show, I think. Did I? No, I think, just give me a moment. I sort of, just give me a moment. I think now I'm ready to share. Yes. Okay. Oh. Okay, everything's set. So this is what you just saw before we went back to the software, total probability of failure. And the next one is what you saw when what I just did to find out that same example, if as an example, 20% of failures are allowed to occur, a bench angle of 49 degree, that's what we saw just now, would be recommended. Now another important design parameter is the minimum bench width. You want to know what is the minimum bench width. Angle, you know, 49 degrees. Minimum bench width. Now, how do you define minimum bench width? It is defined as the total, as the sum of the back break distance and a spill width. Okay, that's the minimum bench width. Now, if this total, this sum is greater than the actual bench width, the actual bench width we took as 7 meters. if this back break plus spill width comes more than bench width, the material will spill over to the bench and move down to the pit and might reach the operating levels, which is not allowed. The operating level where all the mining operations going on. So the back break distance will have a variation because we created that variation. It could be falling, half meter, 1 meter, 1.5 meter, have variation. And spill width also have distribution. So a minimum bench width is defined for each bench angle. Okay, so it will depend on angle. So what we'll do, we will plot the minimum bench width plot. So go back to this. I'm sorry about this. I keep shuffling between this, but that's required. We go back to the software and, oh, no, not this, not this, not this. There's so many things open. Where's the software? Yeah, it's here. Yes. No, not this. What am I doing? I've lost my software somewhere. This should be the one, I think. Yes, found it. So this is the plot we saw. I will go to the main view, which is this one. And what we'll do now, go to statistics, we go to bench design and minimum width. Where's minimum width? Minimum bench width plot. This is what we are going to plot. So this is the minimum bench width plot. Now you see this purple is, as you can see, is the actual bench width, 7 meter we specified. And now since we are trying different bench angles in the probabilistic analysis, we gave 30 to 90 degree. It shows this plot that what is the minimum bench width for different angles. This minimum bench width software has calculated on the basis of the back break cell width and the spill width. So you can see that for an angle, just a minute, and I told you that it should not be less than the minimum width required, which is 7 meters. 7 meter, the mining management told you that 7 meter we require. So your width should not be less than this. Now, what is this value? If I put the sampler here, the value of the angle, it is, you can read it, 48 degrees. 48 degrees, this is 48. So from this consideration, anything which is greater than 40 degree would result in a bench width which is less than 7 meters. Which is, okay, so which means you have to have an angle. In other words, let me explain. I did not explain correctly. If you want to cut it at a higher angle than 48, the minimum bench width required would increase. You will have to have a bench width greater than this. Now, this is what we explain. If I go back again to this presentation. This. So a bench face angle greater than 40 degree would not be recommended because in that case, the minimum bench width will increase more than 7. And of course, as you can see, as the bench angle decreases here, a greater usable bench width is expected. You will have greater width available for you. So this way you can optimize this. Now, the managed approach that you just saw, managed approach, can be used to determine number of failed wedges or the back break distance. It does not provide information on the expected wedge size and amount of bench loss, how much is exactly lost. So for that, you need a quantitative hazard assessment. The another way, which we'll do quickly before we close this, which is called QHA, Quantitative Hazard Assessment. This assessment calculates the probability of the bench failing to a certain back break distance. Okay, this is quite a useful analysis on its own, but can also be linked to the cost of bench loss to calculate the expected risk, the cost of expected risk. Okay. So to interpret the outcome of QHA, Quantitative Hazard Assessment, some terms must first be defined, and then we'll go to that. The first term is cell probability of occurrence. For a given back break cell, we have 20 back break cells. For a given back break cell, This cell probability of occurrence is the number of valid wedges in that cell divided by the total number of samples, which is total number is 100,000. So the valid wedges in that cell. Second thing is cell probability of sliding. It is related to cell probability of sliding. For a given backbreak cell, this is the number of valid wedges which have less than factor of safety 1 divided by the number of valid wedges. So probability of sliding of those ones. Third one is multiplication of 2 for the cell probability of failure, which will give you that the probability of failure of in that cell. Okay, so when you deal with QHA, information on joint persistence should be used, which we'll do now. So in this way, the location and size of the wedge is better determined. So we'll do it now. And now is the time to move back, as the software, the presentation is telling us, to the software. We are coming to the end of it almost. So in case we have something else planned, just 10 more minutes and we'll be done. We share and we go back to the software. Is this the one? I think so. Yes. So we go to back to the software. Okay. So what we'll do, we'll close these graphs which we created earlier. This one and this one. And now what we are going to do is we're going back to the analysis, because we are choosing another form of analysis, and go to bench design once again here. And fixed bench is okay. So what we are going to do it now is we are going to, yes, define as earlier. Now we are going to activate this failure plane resistance. Okay. And we will define a mean value of 3 meters for this tutorial. And a variation exponential. You have to read about exponential variation. We're giving some value. So as I said, you have understood this. Maybe you, once I send this across to you, try it just verbatim on your own, and then you go back to these things for further knowledge. 2 and 6 giving some values. Actually, what this will do, if you read about exponential, they will make sure that the corresponding minimum and maximum persistence value, failure plane persistence will range from 1 meter to 15 meters. That is the persistence value given to it. Okay. So it's okay. This is also okay. Analysis being done. And remember those terms, cell probability of occurrence, cell probability of failure, etc. We look at those now. So go to statistics, go to bench design, go to cell probability of occurrence. In one cell, what is the probability of occurrence of these things? Now, based on the cell, you have these back break distances. You know, in 7 meters of bench width, we have 20 cells. Now, this plot shows you the probability of occurrence of wedges in different cells. So, as you can see that these curves, each of these curves belong to these angles. Remember we gave this range 30 degree to 90 degree, the bench face angles. So they are shown here 30 to 90. For almost all of them, the probability of occurrence, the high probability occurrence is of in this range 0.5 to 1. From the crest, the back break distance, for almost all of them, the peak is in this range. So which is high probability. So highest probability of occurrence is of back break distance lying in this range, 0.5 to 1 meter from the crest. And as you can see, some of these curves which belong to flatter angles, 30 degree, 35, 40, if you look at the legend, they drop very rapidly to 0 probability. But these higher angles, the steeper angle, they go on without coming to 0 to a large distance, which means the probability of larger wedges forming is high on steeper slopes. On flatter slopes like this, the probability quickly becomes 0. But for these steeper slopes, it runs, which means the back break distance, chances of large back break distance, which means large number of wedges being formed on steeper slope, is higher. And this can be seen more clearly in different kind of plot. This thing which I just mentioned, you go back to this, go to statistics once again, go to bench design once again, And now look at the self-cumulative probability of occurrence, cumulative. And this gives you better idea that, you know, these are the slopes, the curves for various angles of bench face. And as you can see, these are the flatter slopes, and then you are increasing steeper. So you can see the probability of occurrence is beyond about 0.51 meter of back break. For this flatter is 0. But for these steeper slopes, which are these ones, you see this is 90 degree, this is 85, 87. For these, even at 3 meter, 3.5, 4 meter, there's a probability of occurrence. So probability of occurrence of larger back break distance is more in case of steeper slope, which is what you expect. So this will let you optimize that. If you want to minimize the probability of occurrence, if you do not want the probability of occurrence of back break more than 1 meter, for example, then this 1 meter, then you would say that I'm okay with this angle, maybe 1.5 meter, or these angles. Purple one is 45, 35, that range, 45 degree, but you have to accept that. Okay. Now, so you understood it. Now let's go to another plot which will give you that for a given back break distance, the probability of sliding of wedge, what is that probability? So for that, we go to another plot, and we go to, you have to do it again, you know, in your leisure time or free time. Go to, sorry, statistics, go to bench design, and we see the self probability of sliding. The occurrence, the wedges occurrence fine, but now sliding. What this curve shows you that probability of sliding in a cell for a given cell. Okay, what is the probability of sliding or failure of those wedges? As you can see, for flatter slopes like this, take for example 30 degree, 35 degree, there's hardly any probability of failure. Okay, only smaller wedges have some probability, but larger, no. Look at this angle, which is also 40 degree. So beyond, say, 1.2 meters, there's hardly any probability of failure. But for steeper ones, like especially, what is this angle? 50, 55. No, this is 50, this is 55, 60. Especially these ones, if you look at these ones, the probability of failure is very high, even for 2 meter, and it continues to be high. Especially these 2-3 curves, you see, top 2-3 curves, 80 to 90, 75 to 90, these ones, they continue to be high for all kinds of back break distances. So we would like to avoid that. If you cut it at 75 or 80 degree, you will see that entire width can be lost. That is the probability of failure happening. Okay. Probability of sliding, failure. Not failure, probability of sliding. So what are the chances of occurrence and failure? Let's combine them. That would be the probability of failure. The previous one was probability of occurrence. This is probability of sliding, if those wedges occur. If you combine them, which means you go back to the last curve, go to statistics, and go to bench design, cell probability of failure. Now you see this curve. You see, imagine you can impress your clients with these curves, not so much. They look so cool, all these curves. What this shows, that probability of failure. And you can see that this is the flat curve. As you go, these are the steeper curves. For these curves, for example, look at the 90 degree one, the last one. It just goes on and on. Even for a back break distance of 4 meter, 5 meter, there is a probability of failure. But these flatter ones are fine. You know, for example, you might be okay, perhaps, to choose this 50 degree angle, because beyond 2 meters or so, the probability of occurrence is zero, you see. So you can be sure if you choose 50 meter, not probability of occurrence, probability of failure. Because formation of wedge, occurrence is one thing. Whether it will actually slide or not is quite another. So this plot combines the probability of occurrence and probability of sliding. So even if wedges are formed, they may not slide. So at about 50 degree, you can be sure that beyond 2.5, 2 meters, it will not extend. The loss will not be more than 2 meters if I choose 50. If on the other hand, you may say, if I choose this 55 degree, I may have to live with a back break distance up to about 3 meters, 2.5 to 3 meters. If I'm able to accept it, we'll cut it 50 degree. Anything beyond that, I mean, especially in this range, you know, this range, I think this one is what should be 75 degree. 75 degree onwards is really tricky, because even 4.55, you can't accept that kind of loss of bench width. So that anyway, and this is specific to the input data that we give. Depending on the mind, depending on the data, etc., you can arrive at these things, and these curves help you take an informed decision, a considered decision, that whether what kind of bench width you choose, okay, and what kind of angle that you choose. And you have looked at both the cases. From the previous managed approach thing, we looked at 49 degree, and when we looked at the bench width, we reduced to 48 degree. So we know that 7 meter width wide bench and 48 degree, that's what we can do for managed. If you apply the same rule, let's look at 48 degree. Where is 48 degrees in this? 50 is this one, this one. So 40 degrees somewhere here, close to 50, which matches actually with this, quite matches. You might live with this. Okay, 40, 50. So anyway, this is how it can help you. And but then this is what we are looking at the bench level. You have to look at this together with the global failure. Remember that I told you that the large scale failure has to be seen, and the large scale failure will also depend on the overall angle of the slope. Overall angle will depend on the bench angles. So you have to look at the mine in totality. And these days, when the analysis tools are becoming so powerful and so easy to run, you might want to look at a 3D, like slide 3D. It's also part of the suite. Slide 3D for an open pit mine. Look at this. But it's so important to look at the importance of these individual benches also. Okay, so this is what I want to tell you. This is all from my side today. Let me stop the share. And it has taken longer time than I expected. And perhaps I speak a bit too much. And you guys are so patient. And so thank you very much. So this is all from my side. Is there anything you want to say or make comment? This is the time now. Otherwise, we say bye-bye. We'll stay in touch for the rest of our lives. That's a promise. The question is that we should keep slope inclination same until the natural surface line reached. What we said for bench height, vertical should we keep? If say, see, as I told you, from practical consideration, see, with these analysis tools being available, and if you have clear data about your geology and structure features on a civil engineering slope, for example, the software tools that you have, they can allow you to design different slopes, angles along the height. But it is not very practical from construction point of view. So you should keep the same slope inclination until and unless the variation is so much, as we discussed yesterday, in conditions in tropical regions where the geology can be very, very different. You have soil and the deeply weathered rock mass and moderately weathered, slightly weathered. In those cases, it is a must to change the angle. And I gave you some example yesterday towards the end of the presentation weathering. I gave you an example that how you can do it. And because there's also a contact between the weathered rock and fresh rock. So except for those cases, for most cases, it makes good sense from the practical consideration point of view to keep the same angle. And to keep the same angle, you should analyze for the worst condition and then keep this same angle. Okay, so as far as possible, otherwise it's difficult, surveying is difficult when you do the blast. Designing and implementing a blast hole pattern is difficult in those conditions. Okay, yeah. Anything else? Nothing? You're very kind-hearted people. Okay, and so if you're joining the webinar, keep your kind-heartedness there also. Don't ask too many questions. Thank you very much. There's a comment that thank you for such an informative session. Thank to all participants. Good luck to everyone. Yes, good luck to everyone. Stay safe, stay happy and healthy, stay positive. There's so much exciting things happening around the world that this COVID thing will pass. Nothing is permanent. This will just go away. But what lies ahead of you is very exciting. You people are in infrastructure sector. And there are some exciting possibilities coming because the world has already built. The easy part is done. Those of us who live in this era, we are going to get some very exciting projects. The only thing is you should be willing. You should be the first to raise your hands. If somebody asks, who is willing to join? Raise your hand. Some very exciting project. And I can tell you from my experience, I've seen a lot of time being in this industry for more than 30, 35 years now. I've seen many things. Now is the time when things are changing very rapidly for two reasons. One is the world is moving, the countries are moving towards projects which were still now considered unbuildable. Number one. Secondly, technologies move forward. The software technologies move forward, which is now there to help you do all this. Plus the communication has become faster, so you can have access to the knowledge. So with all that, I think you're looking at a very exciting time. And so thank you very much, everybody, and see you some other time, somewhere. And maybe sometime we'll be able to meet each other face to face once this coronavirus leaves. Okay, so bye-bye from now, from here for now. And thank you very much.